So start করছি homomorphism. This is basically a part of the graph theory, group theory. What about the homomorphism? So, here we write down the definition. Two groups are there. They have the specific binary operations. A mapping if from G to G dash is said to be a homomorphism if this relation is satisfied. A homomorphism is said to be epimorphism if it is onto. If it is 1-1, homomorphism plus 1-1, this is monomorphism. And a homomorphism of a group from the same group, this is called the endomorphism. Now, we can say homomorphism plus bijective. That means 1-1 and onto. 1-1 plus onto. This is known as the isomorphism, okay? And endomorphism from bijectiveness, that is called the automorphism, okay? Next, we will take an example. Which type of example? Just write it down. Let G be a group and F from a mapping G to G. That means this is an endomorphism defined by f of x equal to x inverse. What you have to show that? You have to show that F is automorphism if and only if x belongs to G. You have to write down if and only if G is abelian. So now we will prove it. Here it can be possible, there you can write it down as x square. So same type of way you have to proceed. So first we will take if G is abelian, then we have to show that this is an automorphism. Let G is abelian. Then what we can write down? X, y is equal to yx, y dot x, or you can understood the composition also. That is, you can just remove this. For xy belongs to G. Okay. Now we have to show that this is an homomorphism. First, we have to show that this is an homomorphism. So for this, let xy belongs to G such that f of x equal to obviously x inverse and f of y equal to y inverse. Now f of xy, that means this is by the definition xy whole inverse. What we know that this is y inverse into x inverse. Now as we know that this is a abelian group G, so we can obviously write it down. So this is fx, fy, that means this is a homomorphism. This shows that this is a homomorphism. So this shows that this is homomorphism. Next, let xy belongs to G be such that fx equal to fy, this implies x inverse equal to y inverse, this implies x equal to y, this implies f is 1-1. Now we have to show that this is onto. Let y belongs to G be such that f of x equal to y, that means x inverse equal to y, that means x equal to y inverse. Also, f of y inverse, that is obviously y inverse, this is equal to y, which is belongs to G. That means for each and every y in the domain set, you can find out the pre-image of it. So this is our conclusion is this is onto. So 1 onto homomorphism from G to G. That means this is F is automorphism, right? As simple as that. So nextly we have to prove the converse part. That is, let F is automorphism. Then we will show that it is an abelian group. G is an abelian. That is, automorphism means f of xy means xy whole inverse, x inverse, y inverse. This means y inverse, x inverse equal to x inverse, y inverse. So as this is holds, that means this is G is, and this is for all xy. So G is abelian, right? Or you can just take the inverse both side. This is also you can do. This is xy whole inverse. This is yx whole inverse. Cancel out the inverse. So xy equal to yx. So G is abelian. So in this way, we can prove it. So similar problem you can also do using it x inverse, changing to x square. Same pattern. Thank you. If you like, then share and subscribe.